Hello everyone. Before coming into software, I used to work as an EE. I was in electronic engineering, and part of that is that I learned some things that I brought with me in software, and I want to talk about that a little bit today. One of the reasons I really like to be in electronic engineering is that electronics is basically about this, right? We take a signal, we use a sensor to transform it into electric signal. That could be anything. It could be light transforming to electricity. It could be sound. It could be a magnetic thing. It could be anything, really. And then you pass this electric signal through what is basically a transformation, right? You transform it into another signal. You modify it in a way that is really precisely defined, and that gives you a new electric signal that you can use to act on the world through an actuator. And what we call an actuator can be anything, right? It can be a little electric engine, it can be a little hydraulic thing, it can be a valve, it can be a little headphones like I have right now. Anything is possible, right? And you get an action on the world. And what I find amazing about that is that I can take anything, any signal, any event in the world, and I can precisely transform it into an action based with some logic. And that's allow me to do so many things in the world, right? That allow us to change the world so much for people, to help them to do so many things. Now, another thing, and most of the magic here happen in the transform function, right? And so let's look a little bit more at it. So what's one of these transform functions? How does it work? How do we make one of them? Well, this is an example of one of them. This is taken from Foon, which you probably know on Twitter. And this is, if I remember correctly, relay-based duplicating punch card machine. It's a machine that takes punch card and duplicate them. And what we can, and that's an example of a transform function from the late 70s. And as we can see here, this function is basically based on a lot of little modules, right? We see them, it's really visible here, that have really precise input and output. And what happens is that each of these modules have a really well-defined function, right? You can define really, really well what they do within well-defined parameters, but usually these parameters are whatever allow human to live, so it's pretty easy to do. And what that means is that if we can know really exactly what is the input, really exactly what is the output, and we can really get these great things about analog electronic, which is that modules have this well-known input and output relationship. We know really well how to compose them, right? We can take two of these things, which we know transform function and we know when we combine them what is a function of the combination. We can compose them. And what that means is that making an electronic transform function, or an electronic system, is basically just plumbing signals between these modules. And that's great. And that's a lot of great things, because it means that we can really easily, relatively, debug what happens. Because at any point in time, I can put a probe on one of these signal, on one of these cable, and I get immediately on my oscilloscope exactly the signal that is in there. There is no real intermediary here, or transformation, or abstraction. I see what is there. And that's great. That allows us to do all kind of nice things. Now, it doesn't mean it's always easy, right? But it means that when this composition doesn't work as you thought, you can always come back and check. Okay, so it's really visible here, right? It works as well in the big, it also works in the small. Even when you have really small components, like here, you can still go and point at any of this pad, any of this time moment, and get the exact signal. It works really well. Now, why do we not do everything in analogic like that then? Because, I mean, if it's so easy to debug, so easy to compose with well-known rules, Doesn't mean we don't make mistake. We make mistake all the time, but when we do, we can try to test and go back for root cause, right? Why don't we do everything like that? Why do you not see this kind of stuff everywhere if you open your electronics component? Well, because there's a few problems with analogic electronic, right? First, there is a problem called noise. And what this is, if you don't know, is basically that every single component you add to an analogic circuit, every single one of them, add some noise. And noise is basically a disturbance of your signal, which accumulate and end up in the point where you don't know what your signal is anymore compared to just random noise. And that's problematic because that limits the amount of components you can put on this. That's a physical boundary to the complexity of your transformation function of a circuit. You can reduce it with better components, more expensive components, but there are limits to it because it's a rule of physics. You cannot beat it. Another problem is that each of these components have a really specific function, right? What that means is that if you want to build anything with it, you will need a lot of specific components capable to do really specific functionalities that are really rare. And what that means is that you get a really complex supply chain. And as we are discovering these days, a complex supply chain becomes really expensive really fast. And that means that even if you make a really simple board, it's going to become really expensive because you have to pay for all this complexity. The other problem is that this is a really slow design cycle because you make your board, you put all your components on it, you test it, it's wrong. Well, now you may discover relatively fast where the problem is because you can debug, right? You can go probe, but you now have to rebuild the whole board. You have to resolder every single component, and that's really problematic. That may take weeks or months. It's not rare. If you spend a lot of money, maybe you can get to a few days, but that's really expensive and rare. And that's a problem because slow design cycle means that it is really hard to upgrade things, to make them better. It takes a lot of time and a lot of money. So, if we look at this, nearly all our problems are in the transform function, right? It's building the transform function and modifying it that is hard and that is making it really expensive. What if this was a reusable component, right? So instead of having all these specific components, we had one big reusable one that could do everything and we could adapt it on the fly so that our cycles are really fast. Well, that's what we do. That's called digital programmable electronics. Most of you may know them as FPGA or microcontrollers, like our Arduinos are an example. And basically the way it works is that we have the same thing, but the transform function becomes something that starts with an ADC, analogic to digital converter, that goes into a programmable microcontroller. Then we do a DAC, a digital to analogic converter that reconverts it to the electric signal that the actuator needs. Same thing, except we now define an ADC, a programmable controller, and DAC as the transform function. And that's your Arduino, right? That's an example. And that's something we can do. You can find them. What is the advantage of digital? Well, there's a few. First, there is a fixed noise. ADC and DAC create some noise, but any digital transformation is noise-free. That's an amazing thing about digital transformation. Your noise is bounded at the start and at the end, and that's it. And you know how much of it you do, so you can deal with it. You can do whatever you want in this programmable thing. So you have an infinite complexity for transformation with no noise, remember. So you can do whatever we want. It's fast and cheap to design because we can just recompile, flash, done. And for the same reason, these components are reusable with near infinite reuse. Right today, we still use and we still put in some of our washing machine and cars and everything, component designed 30 years ago. And still work. We still use the same components that were part of your arcade-born game or consoles games 30 years ago, still are usable like that. Right. So that's great. We have all the advantage we needed, right? We just beat all the problem. Well, what is still there from the great thing about analogic? Well, models with unknown input and output relationship Not anymore, because now you have to deal with the whole memory of the chip, and it has to be all kind of things to allow this abstraction you need, this infinite transformation. So that's not. So let's check what is there with digital. Well, that's not there anymore. Well-known composition function. Well, now we are composing function over the whole memory, and so that we don't really have input and output, so that disappears too, which means that we can't just do plumbing signals between these. Okay, that's bad. We already lost a lot of stuff. But maybe we still have the easy to debug, right? Maybe we can at least get easy to debug back, right? Well, not really. When we work with this and we just plug a probe on a signal, we just get the exact signal that is there, just translated, but with a fairly simple way to translate it. We can see something really, really representative of the signal. But that's not really true when we go to digital. So in digital, we got code on this machine. This code modifies the memory, and the memory is kind of our signal, right? It's the signal that we saw before. But if we want to look at the memory, we have to go through a debug circuit. And then we have to go through a JTAG, which is basically a way to transform this information from the chip to something else, which in this case in our computer. We then have a UI for debugger that we are going to look at this information for, that is going to interpret it. And that's me. I'm looking at this. And this information, the code have changed things, and now my memory went through all that. And I look at the information of the debugger. But that information is not really what's happening on the chip, right? That's just the UI of the debugger. But if I want to understand what's happening in the memory, what the memory look like, I have to revert the model of the debug circuits, right? I have to take the information I get, and I get to pass through an inverse of this debug circuit, right? I have to pass it through a version of this. And then maybe I will be able to get a model of what's happening in the memory in my mind, right? So I have to invert the debug circuit in my mind based on the information I get from the UI, and that gives me an idea what the memory is. Well, that's kind of a problem, because that means, so now to know what is in memory, and to be exact, to know what the code did, I have to go through this revert model. And that's kind of a problem, because it means that I can know about the memory, about what's really happening on the chip, only as much as my invert model of the debug circuit is. If my invert model of the debug circuit is wrong, then I need to fix that. And it's not really easy for me to know if it's the memory that is wrong or if it's my invert function, right? Because nothing can tell me. I only see the memory from the invert, so they are the same thing for me. This, in cognitive, there is a way to talk about that. This is a model offered by Dr. Richard Cook from Adaptive Capacity Lab, and what it tells us is that basically there is this idea of representation. In digital system, in all programmable software system, there is this idea that what we see, the information that our tools and diagnostic tools give us, is a representation. And everything that is under that line of representation, we can never know. And we always have to correct this representation and invert it to be able to understand what's happening. If we look at this one, the representation, the line of representation here, right? Everything that is under that line is a one big thing. We cannot know if it's a debug circuit that we don't understand or if it's our memory not working well. And that becomes even worse, because now that I base my model of memory, I'm going to change my code. Compile and flash it, which is now, I don't know what's there. I flash it, I don't know how it's represented in the memory, and that gives me new code that run. And that's how I know if my invert model of the debug circuit is wrong. That's how I know if this is CPU load or not. Because if my change do not fix the problem, then that means that my problem was not the memory, It was how I interpreted the information I got. So this was Ceci n'est pas un CPU load, because I'm French and I try to stay French. I hope this will enable you to get a model of how we interpret this kind of information like CPU load. And if you want to know more, I am always available for question at all these places. Thank you very much.